Hello everyone. We're going to look at a FM scanner implemented in GNU Radio, and we've done this with minimal coding, only some math within some of the GNU Radio blocks, but no Python blocks, no embedded Python, seeing what we can do with built-in blocks and some basic math operations. This is inspired by a video of a GNU Radio Marine Band FM scanner, and the link to that video is in the description. We're using a Newelec RTL-SDR with a telescoping antenna and a USB-A extension cord. We'll take a quick tour of the flow graph and then see how it works. Across the top of the flow graph, you'll see a number of variables and some GUI widgets or controls for those variables. In the options block, we provided a descriptive name for the flow graph and also used some HTML header tags to make the title larger. There are also two sampling rates, an audio sampling rate of 32 kilohertz or 32 kilosamples per second, and an IF sample rate of 256 kilosamples per second. In addition, there's a variable for the frequency in megahertz, and you can see that this does involve some math that's used to convert some of the other variables to the desired frequency, which will change over time, and we'll see how that is done in a few minutes. The remaining settings are for minimum frequency in megahertz, maximum frequency in megahertz, seconds per scan, scanning step in megahertz, volume for the audio that we'll be demodulating, and a toggle button that will let us select either scan or pause so we can stop if we hear a station that we want to listen to. This flow graph uses two sources. For FM reception, it uses a SOPI RTL-SDR source that interfaces with the RTL-SDR. We use an FM demodulator, and these use the IF sample rate. Now, the output of the FM demodulator is at the audio sample rate, and from there we go through a multiply constant block, which is just to apply the volume control by multiplying by a variable called volume, and on to the audio sync, which interfaces with the computer's sound card. Above that, we have some additional blocks and logic that we use for frequency selection. The goal is to have the receiver scan across a specified range of frequencies. And to do that without using Python code, we've used a sawtooth wave, which has basically a repeating ramp function. We send that through a throttle block at the audio sample rate, and then into a sample and hold block. The sample and hold block passes on the most recent sample of the triangle wave, except when the signal at the purple input of the sample and hold block goes to 0. That signal is controlled by the scan variable, and when scan is set to 0 by pushing the toggle button, the sample and hold block will hold and just send on the most recent sample before that event occurred. From the sample and hold, we go to a probe signal block. This is a very useful block if you want to convert a value in a stream within the flow graph to a variable that you can use in other blocks. You use the probe signal block in combination with the function probe block. The probe signal block is given an ID. We just call it latest sawtooth because we're taking the latest available sample from the sawtooth function. And in the corresponding function probe block, we give it an ID, and that is, in this case, latest sawtooth value, and a block ID for the probe signal block that it will monitor, and that is, in this case, latest sawtooth, the previous block that we saw. It's going to monitor a function that's part of that block, and we'll use the level function, which will give us the current value of the signal that the probe signal block is monitoring. Here I've set the pole rate to 4 Hertz, that's 4 times per second, that the function probe block will check the probe signal block to read the value that's being monitored by the probe signal block. And we'll set the initial value to 0. There are also 2 sinks that are used to monitor the frequency in megahertz. Again, that frequency in megahertz depends on the value of the sawtooth function and some of the other variables. The number sync will allow us to see the frequency change as the scanner tunes through a range of frequencies in the FM broadcast band. The time sync is less informative, so we're actually going to disable it. We'll go back to the frequency megahertz block so that you can see the math that's used to calculate the value of the frequency in megahertz. Next, we'll look at the settings in the signal source block. This is set to output a sawtooth wave with frequency of 1 divided by the number of seconds per scan. It has an amplitude of 1, offset of 0, and in this case, an initial phase offset of pi radians. We'll look at the settings in the SOPI RTL-SDR source. The general settings are to have a complex output type. The sample rate will be the IF sample rate that we've specified in one of the variable blocks. Bias T power is set to false. That would be used to power amplifiers and perhaps other devices that are connected to the RTL-SDR. And the USB buffer size is left in the default setting. None of the advanced parameters were changed. In the RF options, the frequency in megahertz is converted to a frequency in hertz by multiplying it by 1 million or 1e6. Also, the AGC is turned on by setting that value to true. The default value is false. And we had also set an RF gain previously. Now we're going to run the flow graph and see how well the scanner works. It's running in Windows using Radio Conda. You might get better performance with a direct installation in Linux. The flow graph is started. You can see the spectrum in the FM band, and you can see the frequency slowly incrementing from one station frequency to the next.
That is part of the gift also.
There's a volume setting that we can use to increase or decrease the volume.
As unfair.
And
what you see is this kind of creative.
We can use the scan pause button to stop on a station if we want to hear the same station for a while.
It is amazing what occurred in the spread of the gospel. He claimed that it...
So that's a basic FM broadcast band scanner built using GNU Radio and an RTL-SDR with no real Python coding, just some minimal math expressions, and just as an example of what can be done in that way. However, you can do much more if you use Python code in GNU Radio, and you'll see one example of that in the Marine Band scanner linked to in the description.